We have one more talk in this session. It's from, let me just pull up my little schedule here. It's from John Ochab. I hope I'm pronouncing your name correctly.
Yeah, Ochab, yeah.
Ochab, I'm sorry. From Reynolds Community College, and it's entitled Interpreting Reality Bell's Test. John, take it away.
Okay, can you see this?
We don't see anything yet.
You don't see anything yet?
No. You haven't shared.
Oh, I'm sorry. Yes, right. I have to show it. Sure.
Well, you haven't shared your screen yet. Okay, you started sharing. All right, now you're good. Now you're good.
Can you see it now?
Yep.
All right, there you go. Right? You can see it?
Yes.
Yeah, okay, great. All right, thank you. I'm going to have to talk quick because I'm condensing a half-hour talk into 15 minutes. Starting in the early 1920s, a friendly debate erupted between Albert Einstein and Niels Bohr, the father of atomic theory and quantum theory, on the nature of physical reality. However, it is really a debate about the idea of the measurement process of a property of the object. Does measurement dictate the reality of the object being measured? Do the properties of the object exist before they are measured? Quantum theory divides the world into two parts, the system and the observer. The system, that part of the world being modeled, atoms, subatomic particles, had both particle-like and wave-like properties, depending on how one observes or measures them. The system in quantum mechanics is described mathematically as a wave function, represented as a superposition of quantum discrete states that contain all the properties or observables of the system. The coefficients, usually complex, are the possibility amplitudes of obtaining a particular property upon measurement, with probabilities for each property being given as a square of these coefficients. Quantum theory has some strange consequences, as in this 1935 thought experiment by physicist Erwin Schrödinger. A cat resides in a sealed box containing a radioactive source, a hammer, and a glass vial of poison. The probability of radioactive decay when measured by a Geiger counter is random. When the Geiger counter detects decay, a hammer is released, which breaks the glass and kills the cat. This implies that the probability of the cat being dead or alive depends on the probability distribution of the radioactive decay, not a certainty. The property of the cat, the system, is revealed once the box is open, the measurement now being made. So what is the reality before the measurement? Einstein could not accept quantum theory's probabilistic view of the universe. He thought the cat did exist, we just don't have enough information. He recognized quantum theory's ability to accurately predict the results when measuring properties of nature such as energy, momentum, and electron spin, but rejected quantum theory's statistical statements describing the likelihood of different values. He felt any successful theory should provide some understanding of the physical events responsible for those results. He believed there existed hidden variables that would support a more cogent world, and if found, would remove the statistical interpretation of nature by quantum theory. For example, knowing the microscopic behavior of atoms in a thrown pair of die could predict the outcome with certainty, possible in principle, but impossible in practice. He thought quantum theory was really classical statistics in disguise. So here are some of Einstein's worldviews. Realism, physical reality is independent of human observation or measurement. Inductive reasoning can be applied freely. Locality, no influence signal can propagate faster than the speed of light. This is the basis of Einstein's theory of relativity. These local realistic theories make predictions about the outcomes in certain experiments that are in conflict with quantum theory. Werner Heisenberg's uncertainty principle, upon which quantum theory is based, claims these physical observables of a system are not just unobservable, they don't exist at all outside the context of an observation. This deviates from our everyday reality. Consider the three spin components, axial components, S, X, X, Y, and a Z of the spin of the electron. If you decide to measure the X component first and then the Y component, you get an answer. However, if you measure the Y component first and then the X component, you get a different answer. We say that the two components don't commute. They cannot be known simultaneously. In 1935, Einstein challenged quantum theory with a thought experiment published with Nathan Rosen and Boris Podolsky. It went like this. Two particles in close proximity at the source are allowed to separate. Quantum theory says each particle leaving the source has both the spin up state and the spin down state with equal probability of being in either state. The total spin state of the two particles must also add up to 0. Any measurement performed by Alice on her particle would immediately change the state of Bob's particle and vice versa, no matter how far apart they are. No matter what spin axis is measured, there is a strict negative correlation between the spin directions. And there is no classical explanation for this. EPA argued that instantaneous communication between Alice and Bob goes against special relativity, that no signal can travel faster than the speed of light. This violates the locality assumption. The EPR experiment then proved that either there is some hidden variables present before the two particles are released, these variables would contain an infinite amount of information, or particles' properties, position, velocity, polarization, etc., are not real and are undefined until observed. Therefore, quantum theory is an incomplete theory of nature. They defined an element of reality. If an observable property of the system could be predicted with 100% absolute certainty without disturbing the system, then it must correspond to an element of reality. Niels Bohr said that realism and locality premises were incorrect. Measurements results are immediate, without any delay for signal communication. When the particle spins are measured, it is in fact represents a measurement on the entire system of the two particles, regardless of how far apart they move from one another. The two particles initially entangled quantum mechanically right from their source. These wave functions cannot be separated, cannot be represented or talked about individually. The entangled wave function connecting both particles collapses into one spin of the other upon the measurement. So reality only exists at the moment of measurement. Now here's a simplified EPR thought experiment. Each particle separately possesses paired spins, spin up or spin down, and are given off by a source. One particle is detected by Alice and the other by Bob, who are separated far apart. Alice and Bob each have 3 separate detectors set at angles A, B, and C. Each detector can determine if the particle entered is either spin up or spin down. The table shows that there are 8 possible scenarios for particle 1 and particle 2. Observers Alice and Bob subjectively create the properties of the entities they measure rather than objectively, as Einstein purports. Scottish physicist John Bell mediated this Einstein-Bohr debate with his famous inequality, which put a limitation on correlated measurement results. If violated, it would disaffirm the local realistic theory of nature with its hidden variables and support quantum theory. Bell: no physical theory of local hidden variables can ever reproduce all the predictions of quantum mechanics. Quantum mechanical properties cannot arise from our ignorance of local pre-existing hidden variables. Assigning here of hidden variable properties must then be non-local. He said this issue could be settled experimentally. Okay, so since each detector can only measure one spin direction at a time, we must consider the frequency of seeing different combinations of paired spins of each particle. For example, A1U, D1U means that the first particle is detected in detector A and has a spin up, and the second particle is detected in spin detector C with a spin up. And now we'll have to drop the subscripts. So then inside the parentheses, those represent what each separate particle sees. Well, if you look at this and you determine this frequency, you find out that the probability that we get Bell's inequality, which says that the probability that the first particle has a spin up in A and the second particle has a spin up in C is less than the first particle spin up in A and the second particle spin in its detector B, plus the probability that the first particle's detector spin is up in detector B and the second particle's spin is up in detector C. Now, in the famous STERN-GERLACH experiment, a beam of silver atoms was sent through 2 poles, north and south, of a non-uniform magnetic field. It was found that the intrinsic electron spin, S, takes only certain quantized values, S equal to 1/2 h and S equal to -1/2 h, when magnets were oriented along the X, the Y, or the Z axis. H is Planck's constant. Only one component of S of the electron spin can be measured at one time. Heisenberg's uncertainty principle dictates that the measurement of the spin along one axis destroys any knowledge about the particle spin along another axis. One cannot know 2 spin components along 2 different axes simultaneously, and no single detector could measure them simultaneously as well. A real-time Bell test in real time was made using a STERN-GERLACH setup shown here. Particles 1 and 2 each have 3 separate detectors set at 120 degrees apart, with angles A equal to 0 degrees, B equal to 120, and C equal to 240. Each detector can determine the particle entering its spin, whether it's up or down. If we measured the spin orientation of particle 1 at one of the 3 angles in its detector, what is the likelihood that the spin orientation of particle 2 and one of the other 2 angles in this detector will agree with the results of particle 1? Big question. Do angles A, B, and C correspond to simultaneous elements of reality? For example, if we knew that the spin at x at A equal to 0, what is the likelihood that the spins at B is equal to 120 or C is equal to 240 degrees would be the same? This table shows all 8 combinations one could get with this experiment. If A and B are either both up or both down, then pair AB is equal to 1. If A and B yielded up, down, or down, up, then pair AB is equal to 0. The same goes for pairs AC and BC. According to the hidden variable idea, the average likelihood of seeing a match for any pairs must be at least 0.333, 33%, as shown by the yellow cells. You can see that 6 out of 18. In this case, we see that Bell's inequality is indeed satisfied. According to quantum theory predicts the actual value to be 0.25, which is less than the hidden variable prediction of 0.2333. The predicted value of 0.25 determined by quantum mechanics is the square of the cosine of the angle, which is 120, between any 2 STERN-GERLACH detectors, regardless of whether we're talking about AB, BC, or AC. The cosine of 120 is minus 0.5, and the cosine squared is 0.25. According to quantum theory, the average likelihood of seeing a match for any pair must be at least 0.25, and for both up and both down pairs is 0.5. So now Bell's inequality is violated. So who's right? Well, if the results obtained experimentally are not in accordance with 0.33 prediction, assuming hidden variables, and are closer to quantum theory's prediction, then our initial assumption that A, B, and C exist simultaneously must be incorrect. This simulation I'm going to show you shows a source giving off 2 particles in opposite directions, each particle separately possessing paired spins. Okay, so let me show you this. One second. Okay, here we go. Right, do you see this? Do you see that simulation?
No, we don't.
Okay, do you see it? Do I have to share something?
You have to share your screen. You stopped sharing.
Okay.
And also, just for your own sense, you have about 2.5 minutes left.
Okay.
Including the question time.
Right. You see this?
Yes, we see
okay.
this.
So this is a simulation. And now let's assume that the hidden variable theory is correct. So what we're going to do is we have a graph here, and the measurement outcomes are shown by looking at the graph of the probability of opposite spins and paired spins versus the total number of outcomes. Okay, so let's take a look. So clear it, and now we'll continue it. Now you can see what you get with the. You can see you get 0.33, and I'll speed it up for fast forward. So we can see that the probability of getting the same spin is 0.33, as we showed for the hidden variable theory. Okay. Now let's stop this, and quantum's prediction is 0.5. So now let's do the quantum prediction. Okay, clear the measurements. Well, I went a little fast. Let's try again. Okay, here we go. And now you can see it's heading, and I'll fast forward that. You can see that what we're going to get is basically 0.5, okay? Which agrees with the quantum prediction. Okay. Okay. All right. So here's the hidden variable idea that we have product states where the
So
particles.
John, you're not sharing, but you also
Oh,
do
I'm
need
sorry.
to
I'm very
you do
sorry.
need to
Yeah, I know.
but you also do need to wrap up because your time is just about
Okay.
over.
Yeah, that's fine. Okay. Now, this quantum theory was supported in every case for a period of like 20 years. Okay. And there was also ideas of loopholes and everything else. But so there were 10 Bell tests made over actually a 45-year period, and each one more precise than the others, curtailing any loopholes that may have existed during the test, having supported quantum theory in every case. And then there's a famous experiment by Alan Lane, I expect, using the polarization of light. And he also showed that quantum theory is valid. All right, so here are the conclusions. Experiments support the predictions of quantum theory. In fact, as a matter of fact, a different version of Bell's inequality called the CSAAPT equality was what was actually analyzed. So these results mean that our seemingly reasonable assumption of simultaneous hidden variables is invalid. So as it says, for classical composite systems, each of the substances has defined properties, but in quantum theory, there exist states for which the wave function of the composite system is known, but the substances cannot be described in terms of individual wave functions, and thus cannot be described separately. Such states are entangled. Quantum theory explains a particle's attributes only exist within the context of an actual measurement. We must agree with Bohr. The moon reality is not there when we're not looking at it, so to speak. Thank you.
Thank you, John.